Okay, so hi there folks, we're now in our next video in number theory, and we're going to continue our video with what we have talked about in the fundamental theorem of arithmetic. Okay, so we have talked about the first lemma. I forgot to call that the lemma 1, but let's call it now the lemma 1, since we're going to talk about right now the lemma 2. Okay, so this lemma 2 will still be laying the groundwork for our fundamental theorem of arithmetic. We're going to prove this in a later video, maybe in the third, fourth video from this. But yeah, let's start with lemma 2. So this following lemma, this one, extends the result to three or more factors. In our previous lemma, we have only talked about two factors, a and b, but in this lemma, it extends into more than three, or three or more than two, shall we say, factors, using of course, the principle of mathematical induction. Okay, so let's talk about lemma 2 right now. Okay, lemma 2. Okay, so again, a lemma is a statement which will further prove useful in a future statement. So what does lemma 2 say? So let P be a prime number. And we say that P is a factor of this product of numbers a sub 1 times a sub 2 times up until a sub n, where all of these numbers are positive integers. So if this is true, that P is prime and P is a factor, or P divides this product, which all of them are positive integers, um, indirectly saying to us that the product is also a positive integer, then P divides this certain a sub I. Okay, or shall we say P is a factor of this a sub I for some I, wherein I is located within n and positive 1. Okay, so we say that P divides is a factor of a sub I, wherein this a sub I somewhere inside this string of values, a sub I somewhere here. Oops. So we have our a sub I here. Okay, somewhere in between. So let's try to prove that. We're going to make use of the weak induction in proving this. Okay, so let's give the proof. Okay, so we're going to use again by weak induction. So let's write that down. Induction. Okay, so we're going to prove this by weak induction. So notice that when n is equal to 1, oops, let's make use of 1. So the result follows clearly. So it's very clear that if n is equal to 1, so, the results follows clearly that uh, it is true. Follows clearly. Okay, so that's it if n equals to 1. So this is actually our basis step. Okay, this is our basis step. So this prime number can divide 1. It is p is a factor of 1. So shall we say that that's it's equal to 1. So 1 is equal to 1, which is equal to 1. Okay, so assume here, so since 1 is clear that it's true, so we'll assume that it is true. Okay, it is a true for an arbitrary positive integer. Arbitrary positive integer. Um, yeah, integer. Okay, and then we'll call that integer k. Okay, so we say that if p divides a sub 1, a sub 2, up until a sub k, this is the product of all those terms. Okay, then p divides a sub I. Okay, for some I. Okay, so suppose now, say that p divides a sub 1, a sub 2, up until a sub k plus 1. So that is to say, that p divides a sub 1, a sub 2, up until a sub k times a sub k plus 1. So what we did is actually factor out like a sub k plus 1, which is actually true because this is just multiplying. We're just putting a grouping over here. So then by the previous lemma, then let's call that then by lemma 1. By lemma 1. Um, just a recall of what lemma 1 talks about. Let's have a recall for that. Let's call it here. What does lemma 1 say? So lemma 1 just says that if this is in the previous video, if p is a prime, and p divides the product a times b, then p divides a, or p divides b. Continuation of the recall. Okay, so if p is a prime and p is divisible, or p is a product of a times b, then it's gonna be a product of, it's gonna be a factor of a or a factor of b. Okay, as we see here that p is a factor of a sub 1 times a sub 2 up until a sub k times a sub k plus 1. So by lemma 1, it is a product of either this grouping here or a sub k plus 1 separately. Okay, so we're going to use that and apply it here. So if we do, let's show the previous one, suppose there. So if we do, what do we have? So therefore, p divides a sub 1, a sub 2, up until a sub k, or p divides a sub k plus 1. Okay. Now, if shall we say that if p divides a sub 1 times a sub 2 up until a sub k, so therefore then we say that P divides some certain a sub I, because a sub I is surely between this string of factors here for some I. Okay, where, if you want it to be very clear, I is between 1 and k. Okay, so therefore we can say that thus P divides a sub I. Okay, for since a sub I is somewhere between here, since we say from here, okay, that I is between k and 1. So P divides a sub I, okay, where um I again is between, not strictly, between k and 1. Or we can say, or P divides a sub k plus 1. This is still by theorem 1. So in any event, so in any of this event, okay, we say in any event, P, anyways, in any event, P divides a sub I anyways, for some I. Okay, where 1 is, I is between 1 and k plus 1. Okay, so thus by induction we can see that the result here follows. Oops, sorry. So thus by induction, by the principle of mathematical induction, the result holds. The result holds for every integer n. Okay, shall we say for all n in n, all n in n. Okay, that will be our end of proof for this video. Yeah. So this time my pen is kind of shaky since I'm trying a new pen actually, and then I'm checking it out. Maybe it is better than the previous pen, but anyways, here it is. So the lemma 2 states that let P be any prime, and then P is a factor of this big product wherein a sub I is between that, where all of them are positive integers. Then P divides a sub I for some I between 1 and n. So proof by induction, when n is equal to 1, the result follows clearly that if n is equal to 1, so I is equal to 1. So we have the first value, the first um the first term. Okay, so P divides a sub 1, so that's by dilemma 1. It could be, it must be a factor of the first term. So we will assume that it is true for an arbitrary positive integer k. So k for the integers, for the positive integers, we assume that it is true. So if P divides a sub 1 up until k, then P divides a sub I for some I between 1 and k. Suppose P divides all the values a sub 1, a sub 2 up until a sub k plus 1. That is, all of these factors here plus the additional factor of k plus 1. That's for the induction hypothesis. So by lemma 1, we're going to use the lemma 1. We have a recall here. We have recalled that if P is a prime and P divides the product of A times B, then P either divides A or divides B. So we have the or. So from here, we can see by lemma 1 that P divides A sub 1, A sub 2 up until K, or it will divide the other factor, which is K plus 1. So if P divides A a sub 1, a sub 2 up until a sub k, then p divides a, clearly because I, or a sub I, so since um, I is located between 1 and k. So thus p divides a sub I, where I is between k and 1. So or p divides a sub k plus 1. So it's also true to be here, to have it here. So in any event, p divides a sub I, wherein it's really a factor of a sub I for some I where I is between k plus 1 and 1. So by the theorem, or by the principle of mathematical induction, this theorem holds, and it will hold true for all positive integers. Okay, or if you want, for all n and n. Okay, so that's it for this video. Thank you very much for watching. I'm gonna fix my pen now so that we can have a much more better video than next. So thank you very much. See you. Okay, bye.